Many a times, surface cracks appear in induction hardened components, like in this case, a camshaft. Cracks and warping are common defects in heat treatment which are due to excessive and non-uniform thermal stresses during quenching. The solution lied in reducing the heat flux due to spraying of the quenchant. 4 thermocouples connected to data loggers were inserted at strategic locations 5 mm below the surface of one cam lobe. Time temperature data were recorded over one complete cycle of heating and quenching. This data was then used as input to the inverse solver to obtain heat flux due to quenching and surface temperature all along the cam lobe. An analysis of the output data from inverse solver clearly showed excessive thermal stresses developing on the surface of the cam lobe, which led to surface cracks. This was attributed to the cooling characteristics of the quenchant, which was altered by reducing the concentration of the PAG polymer. This case clearly brings out the efficacy of inverse solver, where even surface temperature can be estimated with sufficient accuracy, which is not possible otherwise in practical cases of quenching heat treatment. Inverse solver can be used in all cases where process is inaccessible for direct measurement, for the estimation of metal mold heat transfer for casting simulation, efficient design of water or spray cooling systems, selection of mold coat material and thickness in die casting for increased die life, measurement of contact conductance across metallic or non-metallic contacts, measurement of heat flux in all types of welding, friction welding, etc. for quality control, modeling heat transfer coefficient in boiling, condensation, radiation, forced convection, in space technology for design of heat shields and the like, in nuclear technology for design of complex cooling systems. Inverse solver coupled with the newly designed tool reference quench probe can be used for in situ determination of cooling characteristics of quenchants of all types.